we treated limits. We started with limits, we continued with continuity, and yesterday we touched a bit on differentiation. Today we are going to be looking at the application of differentiation. And as I said, for differentiation itself, the types of differentiation that we are to look at, because it's much, that's what we would be doing at the end, right? And I think I have to say this. Our class is supposed to be 4 days, right? But I'll have one more session with us outside the 4 days. So it will be 5 instead of 4 days. And that one is going to be just practice questions. You get it? So there'll be one more session after tomorrow's session. So let's just anticipate for that one. So application of differentiation. Okay. Now we are going to be looking at a number of theorems, right? A number of theorems, and each of these 3 theorems is examinable. As I said, at the moment, you can have a question that says that state a theorem or state a law or something. It's very examinable. Even if you are not being asked to state the theorem, any question that the theorem is based on will require that you can state that theorem, right? So I know what I'm saying in some way, but let's proceed and we get what I mean. So the first one we are looking at is the extrema of a function. So I'll quickly go through this, then we can do more complex stuff in it. So you have a graph. And this is the function you have. So basically what this extrema something is talking about, right? Let's look at the simplified okay, so this is a graph that we can use. Now the extrema just means that the maximum and minimum values. So if you have a graph with this function, this is a function that you have. The one in blue, that's your function that has been plotted on the graph. The extrema values mean the maximum and the minimum point of your function. So from this graph, you can clearly see that the extrema function, the extrema of this function is f of d, which occurs when x is equal to d, and the minimum is what? F of c, which occurs when x is equal to c. Right, so f of d is the maximum and f of c is the minimum. That's what the extrema is saying. Right, so from the extrema we can get the extreme value theorem. The extreme value theorem says if f is continuous on a closed interval ab and f attains an absolute value f of c, if f is continuous on a closed interval ab, then f attains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d in this interval. So let's understand this. Okay, let me make this smaller. Again, we have a graph. Now, the theorem says that f is continuous on a closed interval. So as I was saying, every theorem has a domain on which it is defined on, right? So it's continuous and also on a closed interval. So the extreme points a and b are both included. So you have a function that goes this way. Let me extend this. The extreme value theorem is saying that if you have a continuous function, and we've seen the properties of a continuous function, but graphically it's a function that we can draw without raising our pen. Once you have a continuous function that is defined in an interval, right? Let's say AB, right? Which value is it? I think they use AB in the definition. Yes, they use AB. Then there will be a point. There will be a point between this A and B that the function attains its maximum and also its minimum. So we can see clearly that. Can you please mute your microphone if you are not speaking? So we can see that from this graph that we have, the maximum value of this function is, let's call this f of c, and the minimum value is f of d. The extreme value is saying that once it is continuous and it is in an interval, you are definitely going to get to a point that the function attains its absolute maximum and absolute minimum. So once you plot this on your graph, this becomes your C value, and of course, this becomes your D. Right? So this is the extreme. So this is what the extreme value theorem is saying. What you have to take note in this is that f must be continuous on a closed interval. Right? This is the condition, and of course, absolute maximum and minimum. So we would be looking at two kinds of extremes, right? We would be looking at local minimum and maximum values and also absolute minimum and maximum values. The difference is that for the absolute minimum or maximum, so let's take this graph for instance, right? So taking this graph for instance, we can see that this is a maximum value. This is also a maximum value because of course the function is rising in this interval. This you can see is a minimum value, but an absolute maximum means among all the maximum values that we have, this is the highest. And a similar something also for the absolute minimum. So all of these are, this and this are both local maximum values. But among the two of them, only this one is an absolute maximum, right? So that's the difference between an absolute, English. That's the difference between an absolute and also a local maximum or minimum value, right? We are going to go through a lot of theorems before we move on to the calculation, right? So please, let's focus on this very carefully. So let's look at the Fermat's theorem. The Fermat's theorem is saying that if f has a relative extremum, right, at c, then either f prime of c is equal to 0 or f prime of c does not exist. So what the Fermat's theorem is, so let's look at an application of the Fermat's theorem. Let me see if the application is here. Okay, so there is no application of the Fermat's theorem over here, right? Okay. Now, okay. So, if you have, okay, so I don't want to use an example because the example is down there. But let me use this example, right? If you throw a ball in the air, okay, it starts from, let's represent this graphically. This is your time, let's say t, and this is your f of t. So let's say it moves from this point, it goes up. Gravity is acting on it. Don't forget that, and it reaches its, why is this straight? It reaches its maximum value, and it begins to drop. Now remember that f prime means derivative. So f prime of x is what? The derivative of x. Now the derivative of x is simply the change in f on the change in x, right? So in this case, t. So let's use the t value. So the derivative is basically a change at a particular point. Now, when a ball or an object is moving up, it reaches a point where it's not moving. That's what we call it's momentarily at rest. So momentarily, I can't spell it. But at this point, it's basically not moving. So at that point that um it becomes it stops moving. The change in F, right? So let's let a change in F be. Let's use distance for this. So let's use d of t, right? So let's use d of t so that it becomes a bit clearer. So since the distance is not changing, but the time is still moving, this distance becomes zero, and the time becomes some value that we are not focusing on because the time is not stopping when the object stops. So at that point, the t becomes a value, but the object stops, so the distance is not moving. Therefore, you get the differential to be zero. And that's a concept that both the Fermat's theorem and the Rolle's theorem is based on, right? So the Fermat's theorem is saying that if F has a relative extremum, right, it goes up at a particular C, then either F prime of C is equal to zero. I think we have to alert how many people in the class. A lot of people. I didn't remind. Can someone please put in the group that the class has begun with the same link? I think people are not aware. Can someone please do that? I don't have my phone with me. Okay, thank you very much. Just a minute. Okay, let's proceed. Um, yeah, so on the Fermat's theorem, right? So again, the ball goes up, it reaches a point that it stops. The time is still moving, but the distance is not being covered. So at that point, the change or the differential becomes zero and it comes down. So that's again what the Fermat's theorem is about, right? So f is a function. If it has a relative extremum at c, then either f prime of c is equal to zero or f prime of c does not exist. I'll come and touch why that does not exist part is added, but in an example, right? So let's look at the extrema of a function. Let's look at the extrema of a function as it been defined here. Okay, so the extrema, there's no definition here anymore. Before you looked at what the extrema is, which is the maximum and the minimum values of a function. Now let's look at the critical number, right? The critical number. The critical number of a function is any number c in the domain at which f prime of c is equal to zero or f prime of c does not exist. Now um, critical numbers actually um, explain their names, right? Now the reason why it's called a critical numbers is because at those points, um, the function changes its state, right? So I don't want to go above what I'm on right now, but when you have a critical number, right? it means that at that point, the function is either increasing, decreasing, is becoming undefined, it's or you are having a curve in the function. So that's basically what critical numbers are. So a critical number of a function is any number C in a domain at which f prime of C is equal to 0, or f of C does not exist. So why again is f prime of C equal to 0 for the critical number as well? Again, let's go to our graph, right? I want us to theoretically view what I'm explaining. Wait, am I recording this class? Okay, I'm recording. So if the graph were to have this behavior, it's moving something like this. Now at this point, the change will be 0. The differential will be 0. F prime of x will be 0 at this curve. So if you have a graph, right, every curve, the differential gives you 0, right? F prime of x gives us 0. F prime gives us 0. So all these points, when you map it to the x-axis, you get the critical numbers. Now, once you have a curve, it means that your function is changing its form. So once your function is changing its form, then we have a critical number. It means it's either becoming minimum, as in this case, it's going down, or it's becoming maximum, as in this case, or it's going down again. So at every critical number, the function changes its form. That's basically the explanation for a critical number, right? So let's go over this. We have a question, and we said that the question is saying that find the critical numbers. F of x is equal to x minus x to the power -3 on. So let's solve this. Let's solve this. There's something I would like to point out in this. So as I was saying in our last class, today we'll be solving a lot of examples, right? So let's prepare. Okay. And also, I haven't forgotten the assignments for last time. I haven't received the solution. So please let's solve them after. I didn't post any assignments because of the videos you have to watch on the differentiation, right? So please let's try and do that. As I said, if you join the class late, there'll be one more session that we practice more questions, especially on differentiation and integration. Find the critical numbers of f of x is equal to x minus 3 x to the power 1 on 3. Find the critical numbers. Again, the critical numbers are numbers you get when f prime of x is equal to 0, or this part is also very important, or f prime of x does not exist. These are the two conditions. Let's find our differential. This is why it's important for your differentiation to be okay, because if your differentiation is not that okay, you might know how to find a critical number, but in the first step you'll get it wrong. Okay, so we have 1 minus, again this is a constant, so we can factor out our constant, differentiate this and add it to our constant. So what's the differential of x to the power 1 on 3? We bring our 1 on 3 in front and we subtract 1 from it. So we get -2 on 3. So we get 1 on 3 x to the power -2 on 3. Again, if there is any part that you don't get, stop me right away so that we can go over it before we proceed, right? So we get 1 on the third root of x squared. So let me rewrite it so that it looks nicer, because this thing is looking some way. So we have let me just use 2 on 3 So we have x to the power 2 on 3 on x to the power 2 on 3 minus 1. So what I've done is I've rewritten this expression. Well, this is basically x to the power 2 on 3, right? So you can separate this. You get x to the power 2 on 3 on x to the power 2 on 3, which is 1, minus 1 on x to the power 2 on 3. Then you are good to go, right? So this is what we have. The critical numbers are the numbers where f prime of x is equal to 0. So when we equate this to 0, what do we get? Of course, the denominator goes away. So we are left with x to the power 3 on 2 minus 1 is equal to 0. X to the power 3 on 2 is equal to 1. X is equal to 1. Right? Because any number to the power 2 on 3 equals 1. So even if you take 3 times 2 to the power 3 times 2, you still get 1. Now the second part, when values that make f undefined. This is why I'm solving this question, because a lot of people leave out the value of x that makes it undefined. So this function, this differential here is undefined when the denominator is equal to 0, because it's a fraction. And we know that for every fraction a on b, it's undefined when b is equal to 0. For every root a, it's undefined when a is less than 0. Which one again is the let's see. Yeah, basically these are the two main ones, right? The one that involves a fraction, the denominator should not be equal to 0. And the one that involves a root, a should not be less than 0. Right? Now, let's proceed. Again, this is a fraction. This is a fraction. So it's undefined when b, and in this case, our b is what? X to the power 2 on 3 is equal to 0. So when x is equal to 0, so our critical numbers are 1, x is equal to 1, and x is equal to 0. Again, when you solve this, you have to conclude that therefore the critical numbers of the functions is x is equal to 1 and x is equal to 0. Please, do we get it? Can we move on? It's like today's class is very quiet. Or hello, please, is it clear?
Please, can you go over again?
Okay, let me go over it one more time. So we are looking at critical numbers, and we are saying that the critical numbers are we get critical numbers when we find the value that makes the function equal to 0, or the values that the function does not exist on, right? So we are given this question and we are being asked to find the critical numbers of this. So the first step that we do is to find the differential of the function. And we got this expression. The reason why we wrote this as this differential in this form is that so that we can easily get the value that that makes the function undefined. Okay, because once it's a fraction, it's undefined. We observe that f prime of x is undefined when x is equal to 0, right? Because when you equate the denominator to 0, you get the function to be undefined. So x being equal to 0 is a critical number, because critical numbers are also numbers that makes the differential undefined. Do we get it? Now, the second one is also values that make a function equal to 0. So how do you get that? You equate the differential to 0 and solve for x. So when you equate this to 0, just as we did over here, um, you know you cross multiply. So this goes away. You send your 1 to the other side, and you get x is equal to 1, right? So let's move on. Let's move on. Again, we have this question here, and it's following the same order. Now, let's find the extreme values of the function. The extreme values of the function. So again, I'm going to take a screenshot of this. Then we are going to go to our board and we are going to find the extreme values. Now, before we solve this, let's look at the graphical representation of this as well. Right? Let's see. Just a minute, please. Um, okay, looking for someone. Okay. To find the extreme values of the function, this function, right? So in about 2 minutes, let's try and see how we can understand this. So we said that we have a graph. Today I'm drawing too many graphs. Can't I draw one and just be copying and pasting? Okay, let me draw it first. This is the graph that we have. This is the graph that we have. Um, I'm trying to reach someone, but I'm not. Okay. So find the extreme values of the function. You have a graph that go. Let's draw f of x. F of x goes something like this, right? It's something like this. Okay. Now, the extreme values are, of course, the values that the function is increasing and decreasing on. Okay, as we've seen uh in the slides above, right? Check something. Okay, they use -1 and 2. This doesn't make sense. Okay. So I was wondering why they give the interval, but it makes a lot of sense. Please, is Elsie in the call? Is Elsie in the meeting? So for the extreme value that we had, right? Remember that f is continuous on the closed interval AB. Then f attains an absolute maximum and maximum value f of c and an absolute minimum value f of d at some numbers c and d in A and B. Now, what I want you to take note of is that it's starting from A and ending at A. Therefore, at A, you can get a maximum or a minimum value. And that's why an interval was included in this function that we had, right? So again, let's find our differential and proceed from there. So what I basically explained is that on this interval at -1, when x is equal to, let's say x is equal to -1 here, and when x is equal to 2 over here. At these extreme points, you can have the extreme values, right? So in between these points, you can have the extreme values. So let's find the critical numbers. So we find f prime of x being equal to 12x cubed minus 12x squared. The value that makes it 0 or undefined. For a polynomial, we know that for any polynomial, the function is defined on from negative infinity to infinity, right? So there are basically no points that this function is undefined on. So we can factorize this as x cubed x squared, right? Then we have x minus 1. And of course, this is equal to 0. So the points are when x minus 1 is equal to 0, and when 12x squared is also equal to 0. So we have the critical points as x is equal to 1, and of course, x is equal to 0. Now, to find the extreme value, so for the extreme values, we are taking the point with respect to x. Right? We are taking the points with respect to x. Sorry, with respect to y. So the extreme value are the values with respect to the y-axis. With respect to the y-axis. Therefore, once you have your critical points, the points that the graph is changing on the x-axis, all you have to do is to find the corresponding value on the y-axis. Let me come again. The critical points that you found, right, are the values on the x-axis that your graph is changing. Now we've gotten x is equal to 0 and x is equal to 1 as points that your graph is changing. Is that doing like this, or doing like that, right? Just changing its value. Now we have to find the corresponding value on the y-axis to see the value of it, right? So we have 0 and 1. So let's put 0 and 1 in our function. We don't put the 0 and 1 in our differentiated function because we are finding the value on the original function that we've been given, not the differentiated something. We are not using that for anything, right? So f of 0 is equal to let's see, is equal to -8. Let me make this a bit smaller. It's equal to -8, and f of 1 is equal to 3 minus 4 minus 8, and this is -12, -9. Is my calculation right? -12. Let's see, let me cross check. Now, so let's draw a table for this. So we have how can we draw this table? We are using the value f of 0 and 0. I want to draw this in a way that, let me see if they drew the table, and there's a way to draw the table for this. Okay, exactly. So the x value horizontal, f of x. Good. So f of x value and the x value, right? And we've done for we have the x values 0 and 1, and also we have to test for the endpoint because the endpoints are also points that the value can have an extreme value, because for the extreme value theorem we've seen that it's defined on a closed interval. That is, the endpoints are also included. Where is it? Let's go back to it again. The extreme value theorem, right? So the endpoint, where is it? Just a minute. F is closed on the interval. As you can see, the endpoints are also included. So in our calculation as well, we have to test for the value at the endpoint. So the endpoints, we have -1 and 2. So let's put -1 and 2 in our original equation. So when x is equal to -1, when x is equal to x is equal to -1, we get 3 plus 4 minus 8, and this is equal to -1. When x is equal to 2, we get 32 minus 8, and this is equal to -8. So we get -1 and -8 respectively. So -1 and -8 respectively. And when x was equal to 0, we got -8. And when x was equal to 1, we got -9. Right? So what's the minimum value? The minimum value is the smallest. So the minimum value is f of x is equal to -9, which occurs when x, I don't write like everything, right? But you have to conclude that the minimum value is f of x is equal to -9, which occurs when x is equal to 1, and the maximum value is f of x is equal to -1, which occurs when x is equal to -1. Right? You have to conclude. Well, as I said, in any problem that you are given, once you solve, you have to conclude. Right? Very necessary. So let's proceed. Let's proceed. Please, is it clear? Can we proceed? Hello, can we proceed?
Can you come
Yeah.
again with the conclusion? I don't
The
know.
conclusion. Okay.
Yeah.
So let me write the conclusion. The minimum value is f of x is equal to -9, which occurs when x is equal to 1. Right. So as I said, conclusions are usually 2 marks. It's some way, yes, but conclusions are worth 2 marks. So it depends on who is marking also. Some lecturers are more strict, but usually conclusions are worth 2 marks. So let me say this again. Please listen to this carefully. This question that we are seeing here, the way I solve this, I might lose marks. Okay, maybe I might not lose marks. But if I started solving this way, please listen to this carefully. If I root f of x is equal to 3x to the power 4 minus 4x cubed minus 8, and I find a differential, please, whatever I've done is already wrong. Because once I write the function again, I have to state the interval -1, 2. Because without this, you are telling us that it is defined on negative infinity to infinity, right? So functions that are defined on intervals, once you are solving, you state the function again, you have to include the interval. Very necessary. So this that I would have done wrong, I just left this out. I've lost 1 mark. Again, this conclusion, I've lost 2 marks. This question will usually be 8 or 7 marks, and I've already lost about 40% of the marks already. Right? But it looks simple. Do we get it? Yes. If you are solving, you don't have to do it. You just have to find a differential and this one. But even before you solve, you have to state that you have to state the extreme value theorem, right? So you don't just find a differential and proceed to solve it. So that's why you have to know what the extreme value theorem is saying. So this is the way you solve this question. Since the function f of x is closed on the interval, what the interval -1 to, then f attains an absolute value c and an absolute so you just replace the a and b with the interval that you've been given, right? So once you solve it, you can say that then our d is this, our c is that, like. But you can also do it this way. It makes full sense, right? If you are solving things like Fermat's theorem, mean value theorem, once you are solving, like, make sure that once you have your answer there, you've literally almost stated what the theorem is and the caveat. Again, what you are being examined on is not that you can find differential equals to 0, find a value like by doing substitution. What you are being examined on is whether you know that for the extreme value theorem, the it works on a closed interval, that is 0 and 2, which is defined in the question, should also be included in the calculation. This is basically what you are being 0 and 2. What is the question? Is this the question? It's not the question. Yes, negative. Where did I get the 0 and 2 from? -1 and 2. Yeah, so they're testing whether the -1 and 2, -1 and 2, that is in the question. You know that you can actually have a maximum or a minimum value at those points. Right. So that's what you are being examined on in this question. Once you know that, the way you solve it changes a little bit. Right. So let's proceed. Probably looked at the Rolle's theorem. We haven't looked at the. Okay, so let's try this question, right? Let's try this question. We have 5 minutes. We are proving this question. Prove that f of x is equal to 4x cubed minus 4x plus 1 has at least 1 0 in the interval 0 and 1. Right? This is what we are solving together. Prove that f of x is equal to this has at least 1 0 in the interval. Okay, so before you solve this, try and have a recap of what the Rolle's theorem is saying. Then you can proceed. Let me take a picture of this. Please, we are all solving this. I'll be expecting the answers in the comment section. Okay. So please, I'll be taking the answers right now. This is what we are solving in 5 minutes. So at 4:54, we'll all make our submissions, please. Oh, okay. I think I didn't share it the last time. Sure, I'll share the slides right after the class. Let me even do so right now. Okay, so please, I'll be expecting answers in the comment section. So I've just sent the slides to the group so you can follow along as we saw. Okay, so I think the application of let me um, application of differentiation. Oh, okay, so I've received one answer. 2 more minutes. Let's all try and solve the question. Okay, I've received one. I'm expecting 2 more. So I'm hearing that 126. I've seen the thing on MIS, right? Is it MIS STS that the time is something. But again, I haven't seen an official message, so I'm not changing the time. We will still continue and do as much as possible, right? Yeah, so hopefully it's confirmed, then you can see how we move from there. But at the moment, we are going to continue with the schedule that we have agreed on. Okay, so I've gotten just two answers. 0 on 3 and 1 on 3. Okay, so 1 more minute. Let's try and solve this. I'm still trying to share the slide, but WhatsApp is messing with me, so it's okay. So let's proceed. Um, let me share my screen. So I've gotten 1 on 1 plus or minus, okay, 3 on 3 as well. Okay. Okay. So I was trying to share the slides, but I've failed the one on the application of differentiation, right? Now, I don't write all this because it will be long. If this is your first time joining us, welcome. I'll share the other 2 recorded sessions so we can watch them. And again, there will be one more session in addition to the one that we've already done. We have to have 4, but because of the because it has been postponed, we'll have one more extra session, right? So we have to show that f of x is equal to x cubed plus 1 plus x plus 1 as exactly 1 within the interval. Right, so this is an application of the IVT and also the Rolle's theorem. I know there is plenty writing in this and it makes a lot of sense. Right, so let's go back. So yesterday we saw the IVT theorem. We saw the IVT and we said that for IVT, this is how the IVT works. Again, we are back to the same point again. Remember yesterday we were discussing about IVT and the Bolzano's theorem, right? The Bolzano's theorem. So let's go over this one more time. I'm going to use the same example. Okay. So you have this rod and you put this section in the fire and it's at 100 degrees and you touch another section the far end and you have that part also being at 40 degrees. You can firmly say that there will be a point in between this 140 that the temperature is at 60 degrees Celsius. This is the IVT. So there will be a value in between the 2 extremes. Now, for the Bolzano's term, it's a type of IVT term. It's a specific case of the IVT term that is saying that now you have a part at 100 degrees Celsius and a part at negative 100 degrees Celsius. There will be a part that the temperature will be at 0 degrees Celsius. Now let's take this graphically. For a function to have a solution, it must be equal to 0. So if you are given a function f of x is equal to 2x plus 1, and you are being asked to find a solution to this function, it basically equates to 0 and find that x is equal to negative 1 on 2. This is what we have. Now, for what was I even talking about? Okay, yes. So for a function to have a solution, we basically equate that function to 0. So 2x plus 1, we equate to 0, we get x is equal to negative half. Now, for the Bolzano's theorem is used for getting that solution. What is this? So with the Bolzano's theorem, right, it's saying that if let's use the example f of x is equal to 2x on the interval we have negative 1 and 2. When f is equal to negative 1, f of x is equal to negative 2. When it's equal to 2, f of x is equal to 4. Now, this is where the Bolzano's theorem comes. As I said, the Bolzano is a type of the IVT. So they can use these two interchangeably. right? But it's supposed to be the Bolzano's theorem. Now, the Bolzano's theorem is saying that because there is a change in sign, then there will be a value in between the -2 and the negative and the 4 that we get 0. Now, as we said, 0 is the solution for every function. Let me go over this again. We looked at IVT and Bolzano. IVT is saying that if you have two values, then if you have two values, right, it's continuous. We are dealing with continuity here. There's no jump, there's no loop, there's nothing, right? If you have two extremes, there'll definitely be a middle number in between the two extremes. The Bolzano is saying that, okay, you have two extremes, but in this case, there is a change in sign. Then there'll be a neutral point, a 0 point in between the two extremes. So we have -1 and 2. These are not the changing sign that I'm talking about, right? It's just an example. Unfortunately, these are also changing signs. But let's use this example, by the way. We have f of -1 giving us -2 and f of 2 giving us 4. There is a change in sign from negative to positive. Therefore, there will be a point. There will be an x value. That value, let's say it's c, that the f of c would be equal to 0. This is basically what the Bolzano's theorem is saying. So let's go back to our question. Now, let me use this solution. Let me not write everything again. It says that show that there is exactly 1 0 in the interval. Now, first of all, to show that a function has 1 0, you have to show that there is a 0. Do we get it? So, how do you show that there's a 0? You slot in -1. You show that there is a. You show by the Bolzano's theorem that there is a c in the interval. So, when you put in -2 into this function, what do you get? You get -8 plus 2 plus 1. And that gives you -5. Does it give you -5? Let's see. -8 minus 2. Let me go back to my board. Please let me take a picture of this. I've already done that. No. So we have to show that there is exactly 1 0. Just 1 0. First of all, we have to show that there is a 0. There is a point that f of x is equal to 0. And how can we show this? By what? The Bolzano's theorem. No, this name is very nice. Maybe I should call myself Bolzano. So having f of -2, we get -8 minus 2 plus 1. This is equal to -9. When f is equal to 0, we get 0 plus 1. This is equal to 1. Now, here is where it gets interesting. There is a change in sign. Therefore, by this man, whose name I think I've stolen, there is a point, let's say f of c, where we would get 0. Because we are changing sign and it's continuous. If you are moving from positive to negative, you will definitely get to make a 0 before you get to your positive, or vice versa, right? So this has proven that there is a 0 for the function. Now the next thing we have to do is to show that there is exactly 1 0, right? And I don't even know the type of proof that has been used in this case, but let's see if this makes sense. By the IVT theorem, there exists in this such that f of c is equal to 0. We've explained that. We said that the IVT and the Bolzano's theorem can be used interchangeably. That is, f has at least 1 0 in the interval. Now, suppose that f has two distinct roots, c1 and c2, and c1 is greater than c2. Then c1 is equal to 0 and c2 is equal to 0. In view of the fact that f is differentiable on this interval, Rolle's theorem leads us to conclude that there exists, or this doesn't make sense to me. Maybe I'm not understanding it, but let me see. Okay, I think I'll have to go and do a research on this part or find a different way to solve this. But what I'm seeing here is not telling me why, So let me just hold on with the part. All right, but we've been able to show the first part, which is that there is a zero in the interval, right? By using the Bolzano's theorem. Now the problem, right? The challenge now is that we have to show that it has exactly one solution in the interval. I'm not going to do that right now. I'll do more research on it and explain it tomorrow, right? Because this thing I'm seeing here is contradicting with what I have. Again, prove that it has at least. So let's take a look at something, right? Where is it? 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 So let me see if my there's 1, 2, 3. Just a minute. Let me Bolzano. Oh, it's not here as well. So the Bolzano's theorem states that there is at least. So for the extreme value, the intermediate, the Rolle's theorem, please take note. There are times that you have exactly one. Let's look at the Rolle's theorem. There exists at least. So this one is saying at least. Let's look at the extreme value theorem. So the Fermat's 2 is saying that there is an extremum at a particular C, just one C, right? So some of these, so extreme is saying that at both C and D, just 2 points. We have to identify the domain on which is being defined on. So for the wait, what am I even talking about? Prove that f of x is equal to 4x has at least. So for the Bolzano's theorem, right? For the Bolzano's theorem that we saw that it has at least, like Bolzano is also at least. It's also one of those cases that you have at least one solution, right? Because once f of x is equal to 0, the number of solutions you get depends on the power of your function. Now this is one similar one to the one we've done up here. This one is saying exactly 1, 0, but this one is saying that it has at least 1, 0, right? At least 1, 0 in the interval. Right. So with this one, before we solve this one, let's go back to the Rolle's theorem and identify something. Okay. Let f be continuous and differentiable on AB. If f of A is equal to B, then there exists a number C in A and B such that f prime of C is equal to 0. Let's come back to our question. Consider the function g of x is equal to x to the power 4 minus x squared plus 1 on a closed interval 0 and 1. Since g of x is a polynomial, it is continuous and differentiable everywhere on the interval, right? G is continuous on 0 and 1 and differentiable on 0 and 1. Now we observe that g of 0 is equal to g of 1. So therefore, by Rolle's theorem, there exists a number in the interval such that it's equal to 0 and so let's see if we can solve this using the Bolzano's theorem, right? Let's solve this together. I was trying to identify a trend in the questions that we have how to identify the method to use, but let's see if we can identify it together. Okay, so we've seen one way that we can use to show that a function has a zero in an interval. We've seen the Bolzano's theorem, how by a change in sign. Okay, now with this one, for 1 0, let's do f of 0. F of 0 is 1, and we have f of 1 to be equal to 1 as well. So we can see that in this case, we cannot use the Bolzano's theorem, right? We can't use the Bolzano's theorem. So there is one, so when f of A is equal to f of B, and also the function is continuous on an interval, then we are back to one theorem, which is what? Which is the Rolle's theorem. F is continuous on this interval and differentiable if f of A is equal to B, then there exists at least one C in A, B, such that f prime of C is equal to 0. Now, the way we solve, there are so many ways that you can solve for an equation, right? Let's take an example. So you have x squared plus, let me know it's plus, x squared minus 3x plus 2. Okay. So with this, x is equal to 1 and x is equal to 2. I'll confirm this with the calculator later, right? But I just for my function. But usually you should get this for the answers. So this is the function that you have. To solve this, you can factorize, right? So by factorizing, let's confirm that this is correct. We can have x minus 1, x minus 2, plus the x cross minus x squared, minus 2x minus x plus 3, to x squared minus 3x. X squared minus, sorry, plus 2. Okay. Yes, so our solution is correct, right? Our solution is correct. So we can use this example. So we have x squared minus 3x plus 2 is equal to 0, right? This is f of x. Can we find the solution in another way? Let's try it. Let's try and find the differential of f of x. We get 2x minus 3. Isn't this will not work? Yeah, this won't work. So I was trying to arrive at a point, but I failed miserably. Okay, maybe the example I used. Okay, so it doesn't hold in the case I was using. Actually, it should. It should hold. Yes, it should. So once you find f prime of x, right, you get 2x minus 3. Then you have to just replace x with your x value. Right, so what was the x value we've been given? We've been given 0 for the x value because this is, please look at the far left. This is x and this is y. So when x is equal to 0, this still doesn't work. I'm very, very, very surprised. Why isn't this working? Wow, 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 wow. Okay, I think I'll have to check this out. I'm trying to make a relation between the Rolle's theorem and something, but it's not working. It's not working. It's not working. It's not working. Okay, so let's solve this another way. Okay, we have f of A being equal to f of B. Right. I'm trying to make a relation, but it's not working, so I'll just move on. Right. The Rolle's theorem is saying that then there exists one number c in AB such that f of c is f prime of c is equal to 0. Okay, so that f prime of c is also becomes the solution, right? So once we have f prime of c, we have to first find a differential of f of x. So f prime of x gives us 8x squared minus 4. So f prime of c gives us
12,
16c squared.
12x squared instead.
12x squared. Oh, okay, thank you very much. 12x squared. Right, what am I writing? Thank you very much. So 12x squared minus 4. So f prime of c gives us 12c squared minus 4. And equating this to 0, we get 12c squared minus 4 is equal to 0. So c squared is equal to 4 on 12, 1 on 3. So c is equal to plus or minus root 3 on 3. Right? I just rationalized. Okay, so this is the value we get for c. And c is in this interval, so it's actually satisfied. So this is the value of c. So because we've done this, let's see how they explain this and how they concluded with their final answer. I'm not really getting how to conclude this. Okay. So now the first thing that we did is that we had to find the value of the function at 0 and 1, right? Once we get a changing sign, we could use the Bolzano theorem, but in this case, we didn't get a changing sign, so we could not use the Bolzano theorem. So we opted for the Rolle's theorem, right? Which is saying that if f of A is equal to f of B, then we can find a differential at a particular point, and we get 0, right? So then we conclude that there is this. So what we actually did was that we were finding the value c that is in the interval, the zeros that were in the interval, but you don't have to do that here. Okay, I was just trying to show that you could actually get your c by finding the differential, and you can actually do that. There's a way to find your c. Maybe the equation I used doesn't hold, or maybe okay, I know why. I was using the interval, right? I was using the interval that we were given, but for you to do this, you have to get a point. You have to get a point and use the point on the graph, right? But I was using the interval, and I'm sure that's why it didn't work. But I'll look more into it for next week's class. It's not that important, but we have to understand what we are doing. Okay. So again, because g of 0 is equal to 0 and g of 1 is equal to 0 as well, f of A is equal to f of B. Then according to the Rolle's theorem, we can literally find the differential, and there will be a point C that the function becomes 0. Okay, so let me basically explain this again. Let me explain this again. Let's go over this again for the last time. Now we've seen that we started with the Bolzano's theorem, right? And we are saying that for the Bolzano's theorem, if you put in f of A and f of B, we are getting a changing sign. This is plus, this is minus. Then there will be a point that we get 0, right? There will be a point that we get 0, which is the root of the equation, right? Now we've also seen the Rolle's theorem. Now we can find the solution. Okay, you can watch a video on it. I'm not getting an equation to use, but you can find a solution for a graph by using for a function by using differentiation. Okay, and Rolle's theorem is basically differentiation that has been glorified. Because Rolle's theorem is basically f of b minus f of a on B minus A. And in the case of Rolle's theorem, f of A is equal to f of B. So basically, so at a particular f of C, let's write this again. At a particular f of C, we get f of B minus f of A on B minus A. This is the formula for differentiation. Like this is the formula for the differentiation. So you are finding the value. So you are finding the value T, right? You are finding the solution. Now, Rolle's theorem is saying that f of B is equal to f of A. Therefore, we know that this numerator is equal to 0. Therefore, we get f prime of C being equal to 0. And as I was saying, you can find the solution of a function using the Rolle's theorem, right? So basically, once you find the differentiation, right, and you equate it to 0, the value C that you get is actually the roots of the equation. Right. Hope what I'm saying is clear. I know it's a bit confusing, but what you have to understand is that we can find the roots by using differentiation as well. And that's what the Rolle's theorem is taking its concept from. Because f of B is equal to f of A, we can just conclude this and we have f of C is equal to 0. Then C becomes the root of the equation. Then we are done. Right. So again, once you show that g of x is equal to 0 and g of 1 is equal to 0, then the Rolle's theorem is satisfied. So there will definitely, please don't store values as we did. You have to conclude. So once you are doing a proof like this and you are applying the Rolle's theorem, remember that in the Bolzano's theorem that we did, we didn't find the roots of the equation. All we had to do was that we had to show that the signs were changing. What is it? We just have to show that the signs were changing. So there is a root in the equation. And that's something similar that we are doing for the Rolle's theorem as well. All we have to do is to show that f of A is equal to f of B. Then there will be a point that the differential of C would be equal to 0. And today it's like we are moving slow, but it's fine, it's fine. Please, do we understand what we did? So let's move on with the mean value theorem. The mean value theorem is the concept from which the Rolle's theorem is gotten from. So let f be continuous on this interval and differentiable on the closed, or on the open interval. Then there exists at least one C such as this. So let's try and understand the mean value theorem because we will be using some examples down there. So again, I'll share the materials to the group again. I have to share it every day because people join every day, so I have to be doing that. So I'll share it again to the group. But if you don't have any of them, please let me know. The one I'm using, the slides I'm using is the slides from a number of years ago, so it might be old. So we have a function that looks something like this. Okay. And as I said, the Rolle's theorem is basically something like differentiation. And the MVT theorem, the mean value theorem, is basically differentiation, right? It's basically the formula of differentiation. This is differentiation. Okay. So let's see how they got this MVT theorem. So we have the this let me use my black pen. We have this horizontal line passing here, and we have this horizontal line as well. Now let's map this onto our graph. So let me style my board a little bit. Let me use green. Yes, let me be stylish a little bit. So let's map this to this and call this C. Let's map to the y-axis. Let's call this f of C. Right. Now let's call this point A, and let's call this point let's call this point B. So this becomes our f of a, and this point becomes our f of b. These are the 3 points that we are having, right? Now, remember from back then that when lines are parallel, right? Wow, so I've actually gotten the pronunciation right. When lines are parallel, they have the same gradient. So from this graph that we have, these two lines have the same gradient. What does this mean? What's the gradient of this line? The gradient of this line, right? The gradient of this line is what? F of b minus f of a on b minus a. Now, the gradient of this line would be the same as this gradient. So, and the gradient at f of c, right? Because we just have 1 point, we can use the differential to find the gradient, because we know that f prime of x is the same as what? Change in x on change in y. So if I can't have the change in x and change in y, I can basically find the differential and represent that as the change in x or change in y. So this can be equal to f prime of c. Let's take a minute and understand what we just done. Two lines have the same gradient, right? F of a, f of b, this line, this line, right? And this line have the same gradient. You can find the gradient using this formula, which is equal to, which is basically the same as differential, right? Because we have 2 points, we can use this formula. But in the case of this line, we have just 1 point, so we can use the differential formula for it. So we know that the differential at the point C is equal to the differential using the point A and the point B. Then that's why we get this equation. And let's look at the application. The reason why I'm going over this, look, I know we can just go over this and solve questions, right? You can basically easily solve all the questions and move on. But believe me, you will not see a question like this. Where is the question? Okay, maybe you see a question like this. Yes, you see a question like that. I'm looking for a typical question that you will never see. You rarely see a question like this, or maybe it will be a bit complicated. Now, mathematics is they like to make it more application. So questions like this, where you have to like apply, because this one they didn't state that use Bolzano, use Rolle's theorem. You have to basically apply what you've learned. And once you can be able to understand how these functions are working graphically, right? It makes it much easier to understand. So this is basically what we were explaining, right? You can, for the MVT theorem, you can, if you look at how we got the formula for differentiation, it's something very similar, right? You have two ways to get the gradient of a line, which is the same as what the differentiation. Once you have 2 points, you can basically use the gradient formula, right? But once you have 1 point, you can just find the differential of it, right? And that's the concept the MVT theorem is based on. So let's basically, I want to look for, there's a question that, okay, it's not here. It's not here. Yeah, so okay, so I think that one is in calculus 2 rather, not in calculus 1. So I'll not be touching it. So well, we've maybe done half of what we have to do today. Wow. Okay, that's fine. Now let's look at, okay, so let's look at this question. Given that f of 0 is equal to -3, f of x, f prime of x is less than or greater than 5. It's less than or equal to 5 for all x. How large can f of 2 possibly be? So with this one, you just do substitution, right? Put it inside and you do this, right? It's a bit simple. We can go over it. Now, increasing and decreasing functions. Increasing and decreasing functions. So a function is increasing if it's basically going up and decreasing if it's coming down. The definition doesn't make sense. Yeah, this is my own definition. Please don't go and write this. This is the definition for increasing and decreasing functions. So if f, the change in x, right? Remember, listen to what I said. If the change in x, if the differential of x, they are basically both the same thing, right? If the change in x, if of b minus f of a on b minus a gives us the same what am I saying? A. If f of b minus f of a on b minus a gives us a value greater than 0, then f is increasing on the interval, right? So calculus, we saw something similar, right? That is in calculus 2. If you want to check if um points are if a function is increasing or decreasing, right? If you want to for example, if you want to use P series or the integration test, I hope we've all done calculus 2, but if you've not done calculus 2, it's fine. We have to check if a function is increasing. And the way we do that is that we basically find a differential of it. The green is not nice. Let me use the black. So if you want to check if a function is increasing or decreasing, you basically find the differential. So let's say 2x, f of x is equal to 2x. So that this function is increasing, all you have to do is to find f prime of x. If f prime of x is greater than 0, sorry, not greater than 0, if it's positive, f of x is increasing then. Right, and I was making a reference to convergence of positive term series, where you have to show that a function is increasing, a function is positive, and it's continuous, right? To show that it's increasing, you find a differential if it's greater than 0. If it's positive, then it's increasing. That's something similar, very similar that we are having, literally the same thing, right? Because f prime of x is greater than 0, in this case, they put in the x, so you are getting greater than 0. But if f prime of x is a positive function, or you put in your x and you got a positive number, which is of course greater than 0, your function is increasing. Right. So basically, this will be the last thing we will be doing to the increasing and decreasing functions. Once we do that, we'll look at the rest of them tomorrow. As I said, I'll have one last final session with us before the test. One last final session, not like the last one, but we can have more than 5, right? It depends, but I want to fulfill the 4, then one last one. Then if there is more time, we can have more as time goes on, right? So where am I? Okay, so increasing and decreasing functions. Increasing and decreasing functions. My microphone is low, so I think I'll be switching. That's why I'm distracted. Sorry about that. Um, okay, so how do we explain this? So first of all, again, let me come back to my graph, my blackboard, and draw another graph. I'm drawing my 5th graph of the day. Right. Now, let's look at this function. Between this point and this point, it's increasing. Between this point and somewhere here is decreasing. Between these two is decreasing. Or between from this place going is decreasing. What am I trying to say? Once you've been given a function, once you have f of x, right, and you are being asked to show that the function is increasing or decreasing, the there will be intervals where the function is increasing or intervals where the function is decreasing. Let me come again. You have a function. It's very difficult for a function to be increasing on all the intervals. It's very difficult. But once you have a function and you're being asked to show that it's increasing or decreasing, it increases and decreases on particular intervals. So how can we get particular intervals? That is where the critical value comes in, because the critical values are points that the function changes its look. Hey, is the class still going on? Like so. Isn't this the mean MVT theorem? Yes, what we were doing before was the MVT theorem. Yes, this is the MVT theorem. That's what we were looking at, right? Yes, MVT theorem was what we were looking at. Before we moved on, I don't know if that's the question you were asking with but yes, what we are doing here is the MVT theorem, right? Please, if you have a question, you can unmute and speak. Okay. So let's move on with the interval A. What's the topic? Increasing and decreasing functions, right? Yes, so let's go over this again. There will be intervals on which the function is increasing and decreasing on. Now, how do you know where in particular the interval is changing? That is where the critical values comes in. So we've been given this function. F of x is equal to x plus 1 on x. F of x is equal to 1. Is it 1 plus 1 on x? Sorry, x plus 1 on x. Right. Now we have to find the critical values. So how do you find the critical values? You find f prime of c. Let's redefine this on c. And let me rewrite this so that it looks simpler. So f of x is again equal to x. Oh, this one will make it more complicated. let me go back to what I was doing before. So f prime of x, right, is equal to 1 differential of x plus the differential of x to the power -1. X to the power -1 differential is -1 x to the power
minus
-2.
1 on x squared.
Yes, thank you very much. So -1 on x squared. This is what we get for the f prime of x. So f prime of c gives us 1 minus 1 on c squared. Again, please don't forget to find a critical value. There are points where the function is equal to 0 or points where it does not exist. Please, that it does not exist, but it's easy to forget. Okay, so this is equal to c squared minus 1 on c squared. So the function is equal to 0 when this differential is equal to 0 when c squared minus 1 is equal to 0. So c squared is equal to 1, c is equal to plus or minus 1. It's only defined when c squared is equal to 0. So c is equal to 0. So therefore, the critical point, right? The critical point that we have is 0, 1, and -1. Let me rewrite this. So -1, 0, and 1. These are the critical points that we have. Now, let's go back to our graph. So now we've gotten some critical points. We've gotten -1, 0, and 1 at the critical point. Now we have to test whether it's in. So we know that in between -1 and 0, the function is either increasing or just decreasing. because there are no other critical points in between our critical point. So once we can be able to show that it is increasing somewhere here, then we know that it is increasing on this interval. Once we can show that it's increasing between 0 and 1, then it's increasing in all this interval. Therefore, we draw something like this. When we have -1, we have 0, and we have 1. Right. Let me see if they use the graph in the. Okay, so they use something like this. They use something different. Oh. Okay. So you can use both of them. Okay, both of them work. Okay, both of them work. So when where's our function? Oh, where's my pen? Our function is f of x is equal to x plus 1 on x. So when f of so when we have f of -1, we get -1 minus 1. Therefore, f of -1 gives us -2. Oh, sorry. Wow. So we will not be using 1. We will not be using 1. And can someone explain why we can't be using 1 to test whether it's increasing or decreasing? Okay, let's go back to our graph. At this critical point, it's changing. So the critical point is basically a point, just one point. So you can't tell if it's increasing or decreasing at this point. It's basically the point that everything changes, right? So you pick values in between your critical points. So I have to add negative infinity and infinity to this one also, right? Let's see if our function was defined on an interval. If it wasn't defined on an interval, then we can use exactly. So we can see clearly that the function was not defined on an interval, right? It's free. It's basically defined on negative infinity to infinity. Once there is no bound, we can basically include negative infinity to infinity, right? So let's pick a value in between negative infinity and -1. So in this range, let's pick -2. Between these, let's pick I want one that will make it very simple for me to solve. Let me pick -1/2, unfortunately. For this one, let's pick half and let's pick 2. Okay. So f of x is equal to x plus 1 on x. When x is equal to -2, what do we get? When x, can someone please help us with the calculation? What do we get? When x is equal to half, what do we get? When x is equal to 2 also, what do we get? Let's see if my calculator is here. But if you've done any of them, kindly let me know. So 2 plus. So this basically gives us, so this is let me -2 plus -2 minus half. This gives us -2.5, which is -5.2. This is work. Let me use my calculator. Just a minute. Negative half. Negative 0.5 minus 1 on 0.5. This is also giving us negative 5.5. So when x is equal to half, so this also gives us 5/2. And when x, so this should also give us 5/2. The values don't matter, but what matters is that this is negative, this is negative, this is positive, and this is positive, right? So from these values, we can conclude that between negative infinity and 1, right? We use the test value -2, so it's decreasing. Between -1 and 0, we use the test value -half, so it's again decreasing. Between 0 and 1, we use the test value half, it's increasing. Between 1 and infinity, we use the test value 2, so it's what? It's increasing because 5/2 is positive. So what's the interval on which it's increasing on? It's not, please pay attention to this. It's not increasing on negative infinity to, it's not decreasing on negative infinity to 0. Like, this is so wrong. You can't write this because the critical points are not part. So basically, we use an open interval where the endpoints are not included. And this is still wrong because -1 is still included in this domain, right? So it's basically negative infinity to your -1, right? And also your -1 to your 0. On this interval, it's increasing, and on that interval, it is decreasing. Let's see what is solved, and let's see if they have something similar to what we did. Okay. So they had -1 and 1 for the critical numbers. What did we get for our critical numbers? We had 0, 1, and -1. So they also had 0 for the critical numbers, yes. But they didn't include 0 when they were speaking of it. So in between negative infinity and -1, it's increasing. Is that what we had? Okay, so there's a problem over here, meaning that our calculation is wrong. Wow. So let's cross-check this. Why is it increasing on this interval? So why is it increasing on this interval? Let's go back and cross-check our solution. We use the test value -2. And -2, just a minute, let me check something. Increasing and decreasing functions. Page 184. Page 184. Session 4B. The function is said to be increasing. Okay, I've sent it. I'll share the book I'm using for us so that we can go over it. Okay. So the the issue that this one is my mistake, right? It's my mistake. So we were using this function to check for whether the function whether the when we got our test value, for example, when we use 2 for our test value, right? We are using this function to check if it's increasing or decreasing on the interval. But that's not what we had to do. We had to use the differentiated function. So we rather had to use, where is it? Our f prime of x is equal to x squared minus 1 on x squared. This was the function we had to use, right? So I'll be sharing the book, then we can do it. I don't think it was written in the slide, so it was written. Okay. So once you insert and it makes sense, right? You get f prime of x being equal to x squared minus 1 on x squared. When x is equal to -2, it's clear that it becomes positive because you are basically squaring a negative. So you get a positive value. So this gives us something positive. The negative half also gives us a negative number because you are basically squaring negative over here. They both become positive, but you are subtracting a very large number. So it becomes negative. You are having half, something similar. You get negative, and of course, this also gives us positive, right? So again, once you get your test values, you don't put it in your original function. Rather, you insert it in your differentiated function to get the interval on which the function is defined. I think we are okay. So I'll end the class over here because I think I'm very, very, very tired. So we'll continue with this tomorrow. We'll be finishing with the application of differentiation tomorrow, right? We will not be looking at sketching a graph because a question has come on it just once. So we won't be looking at it. But once you're able to finish with the application of differentiation, we should move on to differentiation and integration. So we write our test. Okay. Are there any questions? If I've confused you, please let me know. Let me stop share my screen. Let me stop share my screen. Okay. Any questions, please? Any questions? Any questions? Hello, any questions?
Can we get the recording to today's class and yesterday's class?
The recording to today's class. The recording is not available immediately after the class. That's the problem. So it takes time for teams to send me the recording. So I don't get it after the class. So in the morning, somewhere in the morning, because before it becomes available, a few hours after the class, then it becomes available. Do you get it? Yes. So
Okay.
once it becomes available, I'll send it to the group.
Okay.
Okay. And also I'm seeing when is the exams coming on. So so there's something similar that happened last semester last year. The time was changed. Okay, the time was changed. And at the moment, if you check STS timetable up, you see 122 122 on 12. I think it's 12. Yes. And there'll be an email to confirm that as usual, but I haven't received any email, so I don't want to make any announcement on it. Right. So let's equally prepare for the class because for the paper, sorry, because there should be a new timetable that comes in as the final timetable. But the timetable that came in that we got the initial dates from said is the final timetable. So again, we can't tell, but let's prepare for it in case if it's postponed. That's good news. If it's not, we are prepared, so we can just go and write. Right. Yes. So let's have a quick word of prayer. Sorry, any more questions? Any more questions? Again, I've sent the book to the group. Okay, the book is very good. It has 1,000 questions with solutions, so you can go through it and let's. So 1 to 6 class starts at 6:30. Let's not forget, it's still 6:30, right? So just after this class, we have the 1 to 6 class as well. Okay, so if there are no more questions, let's have a quick word of prayer. Then we are done. Father, we thank you for this opportunity. This is our prayer that you grant us understanding. In Jesus' name, we pray with thanksgiving. Amen. Have a nice day, everyone. Bye.